So the thing is that after continuing the previous video, we could state in the way that we need a fundamental timing unit. So oscillator gives a 12 or a 18 megahertz, and we are splitting that into a time series generator and executor, and followed by the dual transfer of data path. So dual transfer of data path is the thing which is shown over here with the watchdog timer as well as oscillator timer. So fundamentally the timer has a split variation of making it into a multiple time stamps. Multiple time stamps in the sense, if you take a single line of timer, so it will generate a clock pulse from transitions like upper and lower, and from 0 to 1, 1, 1 to 0, and 0 to negative 1, and negative 1, from negative 1 to 0. So all these things are a cycle. So when you slice all those things, what will happen is each slicing will contribute to a unique number of things. That is, unique number of things is it is something like how much slices actually we need to use in order to generate it. The more number of slices will contribute to more number of timers available. So with all those timers in concern, what we can do is we can generate more number of data of time space for working with this ALU unit. So on the whole, this gives a complete idea of this PIC 16 microcontroller, stating that it has ports, it has PROM, and it has a RAM, and it has ALU unit, and it has status registers, and it has timers. So timers, datas, and logic units and ports will all together contribute to this PIC 16 microcontroller. So PIC 16 microcontroller will not give things like something to be governed as like a normal microcontroller 8085. The mega picture over here is interrupt generators and things like oscillator setups or power setups. And here interesting thing is the watchdog timer. So this watchdog timer, what it does is it always generates internal clock timer, which means that the internal clock is a countative clock. That means even if you shut down or reset or whatever things you do to this microcontroller, it will initiate the real time clock, that is RTC. Real time clock will be initiated through counts. So watchdog timer is the real time clock which always looks after the entire process. And if an area is lagging timing, or if an area is too much engaged with the timing, these things should be governed in such a manner that the instruction set, which contains address bus and data bus, or address bus alone, or stack pointer registers contributing to address bus. So all these things are maintained in a timer and control unit. If any of the address misses out the timing and control, then it creates a vital problem of instruction overload or overload of execution. So to avoid this overload of execution, the watchdog timer will sense all the timings. If anything is going beyond the timing, so what it will do is it will return a value. Either the return value may be a 0, or the return value must be a data. The data which is being stored or data which is being previously processed, or the data which is being fetched in somewhere else. So it will return some value. It is actually like you're writing a C program, and sometimes you will feel that some invalid numbers or garbage value. If the program returns some garbage value, we will be getting confused to know whether that is a value or something that we have processed. So for removing all these things, or for uh, avoiding all these things, for removing all these things, or for avoiding all these things, what will happen is we need to plan a return value. So that only the C program generates a return 0. So the same way, here watchdog timer will try to synchronize with all the timing workloads, and if anywhere or anywhere else here, if the timer misses the timing sense, then automatically it will start to replicate zero values. So that becomes the basic fundamental save point or checkpoint for all these things. And we have completely gone across all these things with 8-bit or 16-bit registers. So this is the entire idea of this PIC 16 microcontroller. You need to save it in your mind that it has four basic structures. One is input output ports, other is data space, that is PROM, flash PROM, RAM, followed by program counter and stack pointer. I will show you here program counter and stack pointer dealing with this RAM, PROM, EEPROM, and all these things contribute to a mux. A mux is the one which makes the multiple things into a single, that is address and data bus. And the ALU is stored, it processes it. During process, it creates W register or one register, calls it and loads the data. See, it actually loads the data again to the ALU. And ALU has the power to move the data to gain the database, making status register active, that interrupt active, FSR register active, and after that it can either store in data memory or another disk memory. So data is coming inside, it is processed, it flushes out through ALU, and it return back to EEPROM data memory. So here the data is stored, and it updates that data work is completed through status register and FSR register, that is file select register. So what happens is, on returning back, an acknowledgement is given to this, and direct address is also considered, and it is put in RAM. That is, after passing through MUX, it is put in RAM, stating that the process is completed. So the process is completed. So on return back, an acknowledgement is done through RAM and EEPROM, and to do all these steps, there must be another data space, that is PROM, for program counter and stack pointer. So program counter, stack pointer, flash or ROM is an area for contributing to this RAM, and ALU is an area for contributing to this RAM, and acknowledgement for acknowledging FSR register and status register is an area that is finally enabled to store the data in data memory. So on the whole, it is exactly opposite. That is, through mux it enters, and through mux it executes. So mux becomes the difference between execution part, acknowledgement part, and storage part. So hear this video again and again, and you will know exactly the operation of 16-bit microcontroller. Thank you.